Good evening, everyone. I am Manish Ambekar, PMRF and PhD candidate from Aerospace Engineering, ISC Bengaluru. Welcome to the live interaction for the NPTEL course Solid Mechanics. This week we'll be covering some practice problems related to the concepts covered in week 8. In the week 8, Professor Ajit Kumar taught us about extension, twisting, and inflation, extension, torsion, and inflation in the case of a hollow cylinder. We looked at some assumptions which simplified our overall problem, and from there on, we went on to derive the general solution when a cylinder experiences some pressure, is uh, also experiences some torsion as well as some extension forces. Okay, quick check. Is the annotation visible?
Yes, sir, visible.
Okay, thanks. Okay, sorry. Problem number one. Which of the following holds true for uniform extension torsion of a hollow cylinder without pressure? So we are given this is our hollow cylinder. Sorry, yeah, got it. This is our hollow cylinder, and we are told that there is no pressure acting internally, and the hollow cylinder is under uniform torsion and extension. This is what we are given, and we are asked which of the following holds true. So, okay, first of all, we this is the cylinder that this is the case that we are given. So, uniform cylinder, a uniform extension torsion of a hollow cylinder without pressure, and we are asked something about the nature of UR dash and UZ dash. So, if there is, so first of all, in this case, when we use assumptions such as axisymmetry, axial homogeneity, as well as no warping of the cross section, what we end up with is that uz dash, which is epsilon zz, is a constant. Similarly, if pressure is zero, then we end up with ur is equal to minus lambda upon twice of lambda plus mu epsilon zz into r, which means that u dash r is dou u by dou u r by dou r is nothing but minus lambda upon twice of lambda plus mu epsilon zz, and this is Poisson ratio, so this whole thing becomes minus mu times epsilon zz. Epsilon zz is a constant, therefore, and Poisson ratio is also a constant, therefore u dash r also becomes a constant. So, so options B and D are the correct ones here. Okay.
Yes,
So here the formulas in this particular week's you must in this particular week's content you must have noticed that the formulas are a bit involved, but I don't know any other way around it as well. So I guess you'll just have to learn to be comfortable with that.
yes,
Okay, problem number two. Select true or false. Due to the assumption of axisymmetry during extension, torsion, inflation in a hollow cylinder, only u theta depends on theta coordinate. So what does axisymmetry mean? Axisymmetry means that, so suppose this is my axis. Axisymmetry means that a distortion like this doesn't exist. So you'll always have a distortion which is symmetric about the axis as well. So if this is my axis Z and this is my reference this kind of deformation D2 is allowed in axisymmetry, whereas deformation D1 is not allowed. So axisymmetry essentially means that you are u theta and uz are independent of theta. All three components are only a function of r and c. Okay, so this
Yes,
given statement is clearly false.
sir. You have further reduced that you are as a function of R and use it as a function of only Z.
I'm considering simply axisymmetry. Sorry, simply axisymmetry. Okay, axisymmetry would give you this. After this, you have another set of assumptions. So first is say the assumption of axial homogeneity. So axial homogeneity gives us ur as a function of only r. Axial homogeneity, if you remember it, something like this. So after if this is my if this is my reference configuration of the cylinder in ZR plane, my deformed configurations cannot be like this, because in this case my UR at this point, UR at this particular Z is different from UR at this particular Z. So axial homogeneity reduces this. The next assumption that is used is no warping. So no warping means that whatever your cross section is, suppose your cross section is circular, even after deformation, if I show it on a side view, this is what a circle would look like in side view. After deform, and suppose this is your reference, so after deformation, what you have is you cannot have a configuration which essentially looks something like this. That would mean that your circle itself becomes deformed. Say suppose into an ellipse. That no warping condition essentially gives us that uz. So this is the z direction. So uz should be independent of r. So no warping gives us uz as a function of z. So once you combine these three, you essentially end up with what you were speaking about. Ur of r, u theta is a function of r and z, and uz is a function of simply z. This is what you are referring to, right?
Like some twist k which is constant, but that
Hmm.
is not the case. So while deriving the expressions like while writing the strain tensor matrix, we should use that half of 1 by r of dou u z by dou theta plus dou u theta by dou z. We are writing dou u theta by dou z. Their twist is also depend on the z. We cannot simply write dou by l.
Oh,
While
okay.
solving like, I think we should consider that as some variable, not as a constant.
No, so twist. Okay, so I get what you are saying. So twist is different from your shear strain along what is it? Theta z, is it? Yeah, shear strain along theta z. Twist is different. Twist is simply asking this question. Suppose I apply a torsion here and then opposing torsion here. So what is the total rotation of this rod? What is the rate of change of rotation of this rod? That is twist. So twist can be rate of
Is the rate of change can be dependent on the jet, like it cannot be in a constant, like some k
yes,
can
twist
vary.
twist can vary, right? Twist twist can vary, right? Suppose so for a uniform cross section this is okay, but suppose you have a tapered one, and you apply some torsion T here and the other end is fixed. You can figure out with simple free body diagram, if you take a very small cross section, that on either ends of the cross section the torsion that it is experiencing is still T. However, since your area is changing, your polar moment of area j of z is also changing. I write this as the z direction.
Okay.
Okay, And your torsion, if you remember, it's something like Gj into twist, right?
Yes.
So you can clearly see that your twist has to change because your T is constant, G is constant, and J is varying, right? So twist
Yes.
has to be changing.
Yes.
Okay. Problem number 3. For the torsion of a hollow isotropic cylinder, the shear strain gamma theta z and shear stress tau theta z. Okay, so we are given a hollow cylinder and it is under torsion. This is your hollow cylinder. Can you mute yourself? Sorry, because this will be recorded.
Sorry, sir. Sorry,
Yeah,
sir.
it's okay. Okay, problem number 3 for a torsion. Yeah, okay, so this is the hollow isotropic cylinder that we are given, and we are given that only torsion T acts. Okay, so a twisting sort of action will occur in it, and we are asked something about gamma theta z and shear stress tau theta z. So firstly, simply we know tau theta z is G times gamma theta z. This is an isotropic cylinder, so G is a constant. So if you figure out how gamma theta z varies with radius r, your tau theta z also has to vary according to the same. Okay, so I'll start with u theta. U theta we know that it's a function of r comma z. For this particular case, which is a hollow isotropic cylinder with constant torsion T, we can determine u theta to be equal to gamma by L into Rz, where omega is nothing but total rotation, which is say the rotation of right face minus rotation of left face. In this case, your gamma theta z would be equal to dou u theta by dou z plus dou u z by dou theta. For this case, your uz is 0. Therefore, your dou u, and also in general for the assumptions that we are using, uz is independent of theta. Therefore, your gamma theta z is nothing but omega by L into r, and therefore your tau theta z is g omega by L into r. So both, as I mentioned earlier, if you know gamma theta z, you know the nature of tau theta z as well. Both are varying linearly with r. Okay. This
Sir,
is yes.
their gamma theta z I count, and that is for we should use like half of something,
Epsilon
one by r of.
epsilon theta z would be, sorry, I'm sorry, epsilon theta z would be something like this, correct?
Yes. Yes, yes, yes.
Yes. So
Yes.
this is your epsilon theta z. Your gamma theta z is nothing but twice of epsilon theta z. I missed out this factor. But we know that your uz is only a function of z, right? In the cases that we are looking at. So since uz is a function of z, it has no partial with respect to theta. Therefore, this whole term goes to 0. And your dou u theta by dou z ends up determining your gamma theta z, which is nothing but omega by L into r. If this is your gamma theta z, your tau theta z is nothing but g times gamma theta z. So your tau theta z becomes g omega by L into r. As you can see, both of them are varying linearly with radius r. Correct? Problem number 4. For extension, torsion, inflation in a hollow cylinder without pressure, if we know just epsilon r, what can we find? Start with your uz. So there is, in this case, So this is what we are given. We have been told that there is an extension, there is a torsion, but no pressure. Okay, and we are told that we know epsilon Rr. If pressure is equal to 0, then we know that Ur is nothing but minus lambda upon twice of lambda plus nu into epsilon into R, where epsilon is equal to epsilon zz is a constant. Okay, so your epsilon Rr would be equal to dou Ur by dou R, correct? Which is nothing but minus nu times E. So if we know the cylinder, we know the Poisson ratio, we are given epsilon Rr, so we can find out epsilon, which is nothing but epsilon zz. So we can find out epsilon zz. We can also find Ur because we know Ur is nothing but minus nu epsilon into R. So we know these two values. R is a variable, so we know Ur as well, and Ur dash is nothing but epsilon Rr. So to recap, if we know epsilon Rr, when pressure is 0, Ur is nothing but some linear function of Ur is nothing but minus nu into epsilon into R, where epsilon equal to epsilon zz is the constant longitudinal strain along the axial direction, and epsilon Rr becomes nothing but minus nu times epsilon. If we know epsilon Rr and we know the Poisson ratio, we can figure out epsilon, which is nothing but epsilon zz. And since we know the Poisson ratio and epsilon zz, we can figure out Ur as well. And obviously epsilon Rr is nothing but U dash R. Is this clear?
Yes, sir. Yes.
Okay. Problem number 5. If we apply radial pressure to an isotropic hollow cylinder from within the cavity, it will lead to. Okay, so it's a qualitative, it's a question about what displacement mode we'll have. So if we have some radial,
Simulation.
exactly, if we have some radial pressure acting inside the cavity, if we have some radial pressure acting inside the cavity, then this whole structure will inflate. Problem number 6. For case of torsion in a cylinder, we can relate torque T with twist kappa as T is equal to Gj kappa. This is what we were speaking of earlier as well. And in this equation, kappa refers to, so the twist is essentially, as I mentioned earlier, rate of change, rate of rotation of cross section per unit length along axial direction, right? Twist is, if you remember, twist is this. Each of these cross sections will be moving by some, will be rotating little by little. So, okay, so which option is that? Option C. Problem number 7. So in the equation T is equal to Gj kappa, we are asked what J refers to. So J, if you remember, is the polar moment of inertia, right?
The movement of area.
Huh. So do you remember how it is defined?
Yes, sir. Yes, sir. Just like in movement of inertia, but in place of mass, we replace with the area.
So the polar comes from, so you take a small area dA and you look at the radius r, distance r of the small area from the center, and your polar moment of inertia is nothing but r square dA. Right? This is corrected.
Yes.
So J is the polar moment of area of cross section. Problem number 8. The given equation is valid for, so the given equation tau is T is equal to Gj kappa. Is it valid only for hollow cylinders, or is it valid only for solid cylinders, or is it,
I think option B, like we can apply for any type of cylinders with
yes,
variable cross section.
yes. So if I want to rewrite this as a function, so if this is my cylinder and this can be applied to any cross section, so suppose this is Z, so I can write T of Z is equal to G J of Z. Actually, G also can be in general be a function of, right? This J can be varying, which would say that your cross section is varying. This G can be varying, which would tell you that your material itself is varying. And kappa is the twist at that particular location. Okay, so both hollow as well as solid cylinders with variable cross section. Problem number 9. Select true or false. For uniform in extension, torsion, inflation in a hollow cylinder, UR varies with axial strain wherever there is a non-zero internal pressure P, but does not vary with axial strain when there is no internal pressure P. So we'll have to write our expression. UR is nothing but lambda upon twice of lambda plus epsilon plus P upon twice of lambda plus r1 square upon r2 square minus r1 square into r plus p by 2 mu r1 square r2 square upon r2 square minus r1 square. Little bit big, but this is what we have. Here epsilon is nothing but epsilon z, which is the axial strain, and it is constant. We are asked if ur varies with epsilon when p is non-zero, but does not vary with epsilon when p is 0. So the easiest way to go about this is, if we substitute p is equal to 0, then your ur becomes nothing but lambda upon twice of lambda plus nu into epsilon, which is nothing but minus lambda upon twice of lambda plus mu into epsilon z, correct? And into r, sorry, I forgot the r term. Correct. So when P is 0, UR still depends on the axial strain. So the statement is obviously false. And now we move to problem number 10. Consider uniform extension torsion of a composite cylinder made of one material from inner periphery to some intermediate radius and another material Rn from Rn to outer periphery. The two materials have different shear modulus of elasticity. The magnitude of shear stress tau Rz witnesses a jump at the interface of the two materials because of difference in the shear modulus of elasticity on both sides. So if I have to draw this, particular cylinder, I can draw it like something like this. So this is Rm and this is R outer. This is material 1 and this is material 2. And if I have to draw that along the axial, it would look something like this. This is material 1, material 2, okay, and this is Rm. This whole thing is Ro, and this is the center line. So I'll just quickly draw the axis Rz. This is along the r theta plane, Okay, and we are asked about the nature of tau RZ. So, firstly, where would tau RZ act on the boundary? So, this is where the tau RZ would act, right? Is this correct? Is this where tau RZ would act? Am I audible? Or have I made a mistake here? So, this line between 1 and 2, essentially we can think of it as this particular, this is the line between 1 and 2, and we can think it of this particular plane, which would be the R plane, which would be a plane perpendicular to R. And if we have a force acting along the Z direction, if you have a force along Z direction acting here, that would be tau RZ, correct? So tau RZ is essentially the force acting at the interface, along the interface, acting at the interface along the axial direction. And we are asked about its nature, whether tau RZ would be continuous, or as we cross from material 1 to material 2, or would we experience a jump in the jump at the interface because the two materials are different. So, do you know the answer to this? If not, we'll look at a simplified case in Cartesian coordinates. So, suppose this is xy, okay, and this would be, this force would be nothing but tau xy, right? Because the plane normal is along y and the force itself is acting along x. So, this is my tau xy. So, tau xy is acting along the interface. If tau xy just above the interface and just below the interface are different, we would see that there is a force imbalance. So if I write tau xy plus and tau xy minus, so if tau xy plus is tau xy plus is not close to tau xy minus, we would see that just above and below the interface there is large variation in force. As a result, your your material would essentially slip. They would no longer be bonded. Essential condition for like perfect bonding is this, that along the bonding planes or along the bonding surfaces, whatever forces you have, they should be equal to each other. They should be continuous, not equal. They should be continuous, because when they are not, if there is a jump or a discontinuity on the forces which act just above and below the interface, you will have a imbalance and essentially the material will slip. So if you want your material to remain bonded, your stresses along the your stresses acting at the interface should be continuous. Another example of this I could take is that if I look at this sigma yy and I look at points just above and below, right? If I look at sigma yy in the material 1 versus sigma yy in material 2, if they are not, if they are not approximately equal, if there is a jump between them, you can clearly see, right, this interface will tear itself apart. So basically for this case, what you have is sigma yy material 1 should be equal to sigma yy material 2, and tau x of material 1 should be equal to tau x of material 2 at the bonding interface. Okay, same logic you can apply here. If tau rz at a point just above and just below are different, if tau rz at material 1 needs to be equal to tau rz in material 2, because if this case, if if this is not satisfied, your interface would slip, your materials will no longer be bonded to each other. Okay, is this clear? So
Yes, sir.
this statement is false. Okay, if you have any doubts, you can use the discussion forum. Also, if I hope the assignments are okay, right? You are able to solve them, right?
Oh yes, sir. Yes.
Okay, that's good to hear. Anyways, then I think that's that for this week's lecture. Thank you for attending it. Next week we'll be looking at the content from week 9 at the same time, like every Tuesday, 7 to 8 p.m. Thank you.